I'm so glad you found your way here tonight. Your brain is already beginning to prepare itself for something it does every single night. A quiet, extraordinary transformation that most people never think about while it's happening. You'll discover what the sleeping brain actually does for you, and why letting go is the most precise thing you can do. Welcome to Sleepy Mind Science. Wherever you are right now, lying down, eyes heavy, the world beginning to soften at its edges, let yourself be still. Tonight, we'll journey through 100 relaxing facts about the science of deep sleep, from the first quiet slowing of your brain waves to the hidden machinery that clears your mind each night, to the deepest place your body knows how to go. This channel is here for those nights when your mind won't stop moving, when rest feels just out of reach. If Sleepy Mind Science has helped you find that quieter place, subscribing helps us reach more people who need it too. One sleepy soul at a time. You don't need to understand everything tonight. You don't need to hold on to any of these facts. Let them pass through you like slow waves moving through still water. Present, and then gone. Your only task is to breathe, and let the night do what it was made to do. Breathe in slowly. Feel the weight of your body settling now. The night has you. You are already drifting towards something deep and quiet. What is your brain actually doing when it finally reaches deep sleep? Scientists have been asking this question for decades, and the answer, when it finally arrived, turned out to be far more active, far more organized, and far more purposeful than anyone expected. Deep sleep is not an absence. It is not your brain going quiet. It is your brain shifting into a different mode entirely, one that your waking mind never sees, never remembers, and cannot consciously access. Every night, in the first hours after you close your eyes, your brain begins a sequence of biological events so coordinated, so essential, that researchers now believe missing even a single night of deep sleep begins a measurable chain of effects on memory, immunity, and cellular repair. The science of deep sleep is the science of what your brain is doing for you right now. Sleep does not arrive all at once. Your brain moves through it in layers, cycling through stages that each serve a different purpose. There are two broad categories: non-rapid eye movement, sleep, known as NREM, and rapid eye movement sleep, known as REM. Within NREM, there are three stages: N-mut, N-high, and N3. Deep sleep lives in that third stage. N-ba. It is also called slow wave sleep because of the electrical signature it leaves in the brain. When researchers attach electrodes to a sleeping person's scalp and watch the readout, the transition into deep sleep announces itself with unmistakable clarity. The fast, jagged lines of waking thought give way to wide, sweeping arcs, slow, high-amplitude waves rolling through the brain, like a tide moving in from very far away. Those slow waves have a name. They are called delta waves, and they oscillate at a frequency between half a cycle and 4 cycles per second. By comparison, your waking brain typically produces beta waves, cycling between 13 and 30 times per second. The contrast is notable. In deep sleep, your brain slows to a pace that, if it were a piece of music, would feel almost too slow to follow. And yet, that slowness is not passivity. It is precision. Delta waves are the signal that your brain is doing something that waking life simply cannot accommodate. Each rolling wave represents millions of neurons briefly falling silent together, then firing together in a synchronized rhythm that neuroscientists call the slow oscillation. This rhythm is the foundation of everything else deep sleep does for you. The slow oscillation of deep sleep has two phases, and both are necessary. During the first phase, called the up state, neurons across the cortex become active simultaneously. A brief, coordinated burst of electrical activity. During the second phase, called the down state, those same neurons fall silent together. This alternation, activity, then silence, activity, then silence, repeats across the sleeping brain in rhythmic waves. What makes this extraordinary is its scale. The upstate and downstate are not happening in one small region of the brain. They sweep across nearly the entire cortex, moving from the front of the brain toward the back, traveling at a measurable speed, like a wave crossing water. In deep sleep, this wave passes over your brain more than 10 times every minute. One of the most discussed functions of deep sleep is memory consolidation, the process by which experiences from the day are stabilized and transferred into long-term storage. This doesn't happen randomly. During deep sleep, the hippocampus, the brain's short-term memory hub, a small curved structure tucked deep inside each hemisphere, begins to replay the neural patterns from the day's learning. These replays happen in precise coordination with the slow oscillations rolling across the cortex. Think of it as a carefully timed conversation. The hippocampus speaks, and the cortex listens and begins to inscribe. The information is moved from temporary storage to a more permanent address, one less vulnerable to disruption. Scientists have measured this transfer directly, watching specific memory traces reactivate during slow-wave sleep in patterns that match the original learning experience. Sleep spindles are another feature of deep sleep's architecture, arising primarily in stage N2, but continuing into N3. They appear on brain recordings as brief bursts of oscillating activity. Tight, rhythmic ripples lasting 1 to 2 seconds. Flickering at 10 to 12 cycles per second, they are named for their shape on the readout, thin in the middle, wider at the ends, like a spindle of thread. Sleep spindles are generated by the interaction between the thalamus and the cortex, two brain regions in constant dialogue during sleep. Their function is dual. They help protect sleep from disruption, acting as a kind of gate that keeps sensory intrusions from reaching consciousness. And they appear to play an active role in binding memories, linking what was learned today to what was already known. Growth hormone follows a precise schedule, and deep sleep is its signal. The largest single release of growth hormone in the entire 24-hour cycle occurs during the first bout of deep sleep, typically in the first 90 minutes of the night. This release is not incidental. It is triggered directly by slow-wave activity. Growth hormone does not merely build muscle in children. In adults, it directs cellular maintenance across the body, repairing damaged tissue, restoring the integrity of blood vessels, supporting the immune system's first lines of defense, and regulating the metabolism of fat and protein at the cellular level. If deep sleep is reduced or fragmented, this release is diminished. The body receives less of the signal it needs to repair itself. The work of restoration, which only happens here, is left unfinished. Your immune system does some of its most coordinated work during deep sleep. Cytokines, small signaling proteins that regulate immune responses, are produced and released in higher concentrations during slow-wave sleep than at any other point in the day. Some cytokines promote sleep directly, creating a feedback loop where the immune system encourages the body to rest precisely when rest will benefit it most. Studies of people deprived of deep sleep consistently show reduced immune function, lower antibody responses to vaccines, reduced natural killer cell activity, and heightened inflammatory markers in the blood. The relationship between sleep and immunity is now understood to be bidirectional. Illness disturbs sleep, and disturbed sleep increases vulnerability to illness. Deep sleep is when the balance is restored. Body temperature drops during deep sleep, and this drop is not accidental. It is part of the signal that initiates the sleep state. In the hours before sleep, core body temperature begins a gradual decline, driven by heat loss through the skin. By the time delta waves appear in the brain, core temperature has typically fallen by 1 to 2 degrees Fahrenheit from its daily peak. This cooling serves multiple purposes. It slows the metabolic rate, reducing the brain's energy demands and allowing restorative processes to proceed without competition. It also appears to directly support the generation of slow waves. The brain achieves its most synchronized oscillations more readily in a cooled state. This is part of why sleeping in a cool room tends to promote deeper, less fragmented sleep. The glymphatic system is one of the most significant discoveries in sleep neuroscience in recent decades. In 2013, researchers at the University of Rochester described a previously unknown waste clearance network in the brain, a system of fluid channels running alongside blood vessels that becomes markedly more active during sleep. The name combines glial cells, the brain's support cells that form the channels, with lymphatic, reflecting its similarity to the body's lymphatic drainage system. During waking hours, the brain produces metabolic byproducts, cellular debris, used proteins, and waste molecules that accumulate in the spaces between neurons. During deep sleep, the channels of the glymphatic system widen, and cerebrospinal fluid flows through them at an accelerated rate, flushing these byproducts out of the brain and into the body's broader circulatory system for disposal. Among the waste molecules cleared by the glymphatic system during sleep, two have received particular attention: amyloid beta and tau. These are proteins that, when they accumulate in the brain over years and decades, are associated with neurodegenerative changes, including those seen in Alzheimer's disease. Animal studies, primarily in mice, have demonstrated that glymphatic clearance of amyloid beta increases during sleep compared to waking, and that sleep deprivation leads to measurable buildup. Human studies using imaging and cerebrospinal fluid sampling have supported the association, though the full causal relationship in humans is still being mapped. Scientists are careful to note that the evidence is strong, but the mechanism is not yet fully characterized in people. What is clear is that sleep appears to be when the brain takes out its own waste, and one restless night leaves more of it behind. One of the counterintuitive things about deep sleep is how difficult it is to enter from a state of emotional arousal, stress, anxiety, and hypervigilance. States that involve the activation of the body's threat response systems actively suppress slow-wave sleep. The hypothalamic pituitary adrenal axis, or HPA axis, regulates the release of cortisol, the body's primary stress hormone. Elevated cortisol in the evening and early night delays and reduces slow-wave sleep. This creates a biological explanation for something many people experience. The harder you try to sleep, the less deeply you sleep. The aroused nervous system is not incompatible with sleep entirely, but it is incompatible with the quiet, synchronized oscillations of the deep stages. The brain cannot hold both at once. The first 90-minute sleep cycle of the night contains the most deep sleep of any cycle. As the night continues, each successive cycle contains progressively less slow-wave sleep and more REM sleep. This means that deep sleep is heavily weighted toward the first half of the night, while the dreaming of REM is concentrated in the second half. A person who goes to bed late consistently, even if they sleep for the same total number of hours, may get significantly less deep sleep. Because the early cycles, which are richest in slow-wave activity, occur at an unfavorable point on the circadian schedule, the body's internal clock, the circadian rhythm, and the sleep pressure system that builds throughout the day both influence the timing and depth of slow-wave sleep. Sleep pressure, the biological drive to sleep, is regulated by a molecule called adenosine. As you move through the hours of wakefulness, adenosine accumulates in the brain, binding to receptors that progressively slow neural activity and increase the sense of sleepiness. When you finally sleep, adenosine is cleared. Deep sleep, particularly slow-wave activity, is the most efficient way to discharge this pressure. The relationship is measurable. The longer you have been awake before sleeping, the more intense your slow-wave activity in the first cycle, and the more rapid the discharge of adenosine. This is why a brief afternoon nap, while helpful, can reduce the intensity of slow-wave sleep at night. It has already begun to relieve the pressure that would otherwise concentrate into the early deep sleep cycles. Caffeine works by blocking adenosine receptors. It does not reduce adenosine production. The molecule continues to accumulate as usual, but it prevents adenosine from binding, masking the signal of sleepiness. When caffeine is eventually metabolized and the blockade lifts, the accumulated adenosine binds all at once, producing the familiar crash, more relevant to deep sleep caffeine consumed in the afternoon, even 6 hours before bed, has been shown in research to reduce slow-wave activity measurably. Participants who had caffeine at 3 in the afternoon showed significant reductions in deep sleep quality, even when they fell asleep at their normal time, and felt no difficulty doing so. This means the disruption to deep sleep can happen silently, without any subjective sense that sleep was disturbed. Alcohol is often perceived as a sleep aid because it accelerates sleep onset and can increase slow-wave activity early in the night. But the second half of the night tells a different story. As the body metabolizes alcohol, a rebound effect occurs. The nervous system, which was suppressed, becomes more active. REM sleep is particularly disrupted, but late-night slow-wave sleep is also fragmented. Overall, sleep architecture is altered in ways that reduce the restorative quality of the night, even when total sleep time appears normal. This is why sleep after alcohol can feel heavy and full yet leave a person unrested in the morning. The quantity of sleep was present. The depth and continuity of its architecture was not. As people age, the amount of slow-wave sleep they obtain each night declines. This is one of the most consistent findings in sleep science. In young adults, deep sleep typically accounts for 15 to 25% of total sleep time. By middle age, that proportion has often fallen to 10 to 15%, and in older adults, it may drop further still. The neurons in the prefrontal cortex, the region most closely associated with generating slow waves, show a gradual reduction in density and connectivity across the lifespan. This is not pathology in the ordinary sense. It appears to be a normal feature of brain aging, but it helps explain why older adults often feel that sleep no longer restores them the way it once did. The deep sleep they are obtaining is genuinely less. Exercise has one of the most consistently documented effects on deep sleep of any behavioral factor studied. Regular aerobic exercise, particularly exercise performed in the morning or early afternoon, is associated with increased slow-wave sleep, reduced time to fall asleep, and better subjective sleep quality. The mechanisms are still being studied, but several pathways have been proposed. Exercise increases adenosine production, boosting sleep pressure. It reduces cortisol over time, removing one of the primary suppressors of slow-wave sleep, and it may promote the growth of new synaptic connections in the brain, which in turn require slow-wave sleep for consolidation. Notably, the sleep benefits of exercise appear to be cumulative. They build over weeks and months of consistent practice, not from a single session. In the early 1990s, researchers made a discovery that permanently changed how scientists think about sleep and the brain. They found that neurons in the cortex of sleeping rats were replaying the firing patterns from a maze-running task the animals had completed during the day, and doing so during slow-wave sleep, at a speed approximately 20 times faster than the original experience. This was the first direct evidence that the brain uses sleep to actively process the day's events rather than simply pausing. The phenomenon, now called memory reactivation or sleep replay, has since been documented in multiple species, including humans. It appears to be a mechanism by which the brain decides which experiences to preserve and begins the process of integrating them into existing neural networks. The prefrontal cortex, the region of the brain most associated with planning, decision-making, and emotional regulation, is one of the areas most dependent on slow-wave sleep. Sleep deprivation studies consistently show that the prefrontal cortex is among the first brain regions to show reduced function when sleep is disrupted. This has measurable consequences. People with reduced deep sleep demonstrate impairments in working memory, difficulty suppressing irrelevant information, greater emotional reactivity, and reduced ability to assess risk accurately. These effects can persist and accumulate across multiple nights of insufficient deep sleep, even when the person has adapted to feeling only moderately tired. The subjective sense of coping can persist, while the objective performance continues to deteriorate. The sleeping brain is not disconnected from the outside world. It continues to process sensory information and make decisions about what to let through. During deep sleep, the thalamus, a central relay station for sensory signals, dramatically reduces the flow of information to the cortex. acting as a gating system that protects the sleeping brain from disturbance. This is one reason why it is so difficult to wake someone from deep sleep. Sounds that would easily rouse a person from light sleep, or REM, may go entirely unregistered in N3. The brain has, in effect, drawn a curtain between itself and the world, not because it is resting, but because it has more important work to do. The sensation of waking disorientation, sometimes called sleep inertia, is most pronounced when a person is woken from deep sleep. In this state, which can last from a few minutes to nearly an hour, cognitive performance is temporarily impaired, reaction times slow, working memory is reduced, and thinking feels effortful and fragmented. This is not caused by insufficient sleep. It can happen even after a full, restorative night. It is a consequence of the disruption itself. The brain was in the middle of a synchronized deep sleep process when it was forced to shift abruptly to waking. The more deeply into slow-wave sleep the person was, the more pronounced the inertia. The brain needs time to reassemble its waking architecture after being pulled from the depths. Sound has been explored as a tool for enhancing deep sleep without medication. In recent years, researchers have experimented with a technique called acoustic stimulation during sleep. Playing brief, rhythmic sounds, precisely timed to the upstate of slow oscillations while a person sleeps. Early results, published in journals including Nature, Human Behavior, suggest this targeted stimulation can increase the amplitude and consistency of slow waves, with corresponding improvements in memory performance and subjective sleep quality the following day. The sounds used are subtle, soft clicks or tones, timed to match the brain's own rhythm rather than impose a new one. The brain appears to accept these gentle reinforcements and incorporate them into its existing slow-wave architecture. Research in this area is ongoing. Body position influences slow-wave sleep in subtle but documented ways. Sleeping on one side, particularly the lateral position, has been associated in some research with more efficient glymphatic clearance compared to sleeping on the back or stomach. The proposed mechanism involves the geometry of the glymphatic channels in the lateral position. Gravity and fluid dynamics may combine to facilitate the flow of cerebrospinal fluid through perivascular spaces more efficiently. This finding has generated interest among researchers studying neurodegenerative disease risk, though the evidence in humans remains preliminary. What is consistent is that physical comfort supports deeper, less fragmented sleep overall, and that physical tension, whether in the jaw, the shoulders, or the lower back, tends to keep the nervous system slightly elevated, away from the deeper stages. In children, slow-wave sleep is at its deepest and most abundant. Young children can spend up to 40% of their total sleep time in N3, compared to 15 to 25% in young adults. This high proportion of deep sleep in childhood is thought to be related to the intense synaptic growth and pruning that characterizes early brain development. During slow-wave sleep, a process called synaptic homeostasis occurs. The brain strengthens the connections most used during waking and weakens or eliminates those that were not. This prevents the brain from becoming overloaded with weak, redundant connections and ensures that the neural architecture sharpens as it grows. Deep sleep, in this sense, is not just restoration. It is construction. And here, you can allow your body to become a little heavier. Feel the surface beneath you, the support that has been there all along, holding you without effort, asking nothing in return. Your brain is doing exactly this right now. Not pushing, not solving, just receiving, just moving through its slow, quiet cycles, exactly as it was made to do. You don't have to understand it. You don't have to help it. You only have to stay here, in this stillness, while it does what it has always known how to do. The relationship between deep sleep and emotional memory is one of the more nuanced areas of sleep research. Not all memories are treated equally during the night. Emotionally significant experiences, those tagged with strong feeling, appear to receive preferential processing during sleep. Research has shown that emotional memories are more likely to be retained and consolidated than neutral ones, and that sleep, particularly deep sleep, plays a role in this prioritization. But there is another layer. Deep sleep also appears to strip away some of the emotional intensity from difficult memories while preserving their factual content. The memory is kept. The acute pain attached to it is softened. This is thought to be part of why time, and the sleep it contains, helps regulate emotional responses to hard experiences. Deep sleep affects the regulation of appetite and metabolic hormones in ways that have only become clear in recent decades. Two hormones are particularly relevant: leptin, which signals satiety, and ghrelin, which signals hunger. Studies have found that sleep deprivation, including selective reduction of slow-wave sleep, is associated with decreased leptin and increased ghrelin, a combination that promotes hunger, particularly for calorie-dense foods. Even a single night of significantly reduced deep sleep can shift these hormones in measurable directions. Over time, chronic sleep deficiency has been associated with higher rates of obesity, metabolic syndrome, and type 2 diabetes. Independent of other lifestyle factors, deep sleep appears to be part of the biological system that regulates how the body reads and responds to energy availability. The brain during deep sleep undergoes a process that has been described as synaptic downscaling. During waking hours, as you learn, perceive, and experience the world, synaptic connections across the brain are strengthened. This strengthening is adaptive. It is how learning works, but it cannot continue indefinitely. If every synapse were continuously strengthened, the brain would eventually become saturated, unable to encode new information against the background noise of everything already stored. Deep sleep addresses this by selectively weakening synapses. Not all of them, but the ones that were least reinforced during the day. The result is a recalibrated, refreshed network that wakes the next morning with more available capacity. This theory, called synaptic homeostasis, was proposed by neuroscientists Giulio Tononi and Chiara Cirelli, and has substantial experimental support. The heart rate slows during deep sleep to its lowest point of the day. Blood pressure also drops, sometimes by 10 to 20% compared to waking levels, a phenomenon researchers call nocturnal dipping. This regular period of cardiovascular rest is now understood to be genuinely protective. People whose blood pressure does not dip during sleep, a condition called non-dipping, have higher rates of cardiovascular events, including stroke and heart attack, than those whose blood pressure follows the expected pattern. Deep sleep appears to be a key driver of nocturnal dipping. Studies suggest that fragmented sleep, which reduces time in the deeper stages, also reduces the magnitude of blood pressure decline, potentially contributing to cardiovascular risk. Over time, the brain does not simply replay memories during deep sleep. It appears to do something more creative with them. During the slow oscillations of N3, the hippocampus repeatedly reactivates recent memories and sends them to the cortex. But the cortex does not store them in isolation. It integrates them with existing long-term memories, finding structural similarities, noting patterns, linking new information to older frameworks. This integration process may be the neural basis of insight, the experience of waking up with a solution to a problem that seemed intractable the night before. Researchers have documented this experimentally, demonstrating that people who sleep between exposure to a problem and an attempt to solve it are significantly more likely to find hidden solutions than those who remain awake. The kidneys slow their filtration rate during deep sleep, concentrating urine and reducing the body's need to wake and urinate. This is partly regulated by antidiuretic hormone, which is released in higher amounts during sleep. It is one of many examples of the body's systems coordinating with sleep, rather than simply pausing during it. The biology of sleep involves the synchronization of dozens of processes: hormonal, immune, metabolic, neural, all timed to occur during specific phases of the sleep cycle. Deep sleep is not a passive state waiting to be filled. It is a window of biological activity that the rest of the body's systems have evolved to use. The term slow-wave sleep was coined to describe the brain's electrical activity, but the slowness extends beyond the brain itself. During N3, muscle tone decreases to near paralysis levels in some regions. Breathing slows and becomes more regular, and the variability in heart rate, normally quite high during waking, diminishes significantly. The body, like the brain, settles into a slower, more synchronized rhythm. This coordination is notable the nervous system, the endocrine system, the cardiovascular system, the immune system, and the metabolic system are all running at a pace and in a mode that waking life does not and cannot replicate. Deep sleep is the biological analog of turning off every non-essential process to focus on maintenance. Learning a new physical skill, playing an instrument, mastering a sport technique, practicing a craft, depends on deep sleep in ways that researchers have carefully mapped. Motor memory, the encoded knowledge of how to perform a physical action, consolidates during slow-wave sleep through a process distinct from the consolidation of declarative memory. Sleep spindles, those brief bursts of activity in N2 and N3, appear to be particularly important for motor consolidation. Studies of musicians, athletes, and surgical trainees have shown that sleep between practice sessions improves performance more than an equivalent amount of additional waking practice. The improvement is not merely rest from fatigue, something specific to sleep, to the deep phases in particular, is doing the work. The role of deep sleep in pain regulation has become clearer over time. Slow-wave sleep affects the sensitivity of pain pathways, and disruption to N3 is associated with lower pain thresholds, meaning that after a night of poor deep sleep, the same stimulus registers as more painful. This effect has been documented in healthy adults, after a single night of sleep deprivation, and it accumulates with chronic sleep deficiency for people already living with chronic pain conditions. The relationship becomes circular. Pain disrupts sleep, and disrupted sleep amplifies pain. Restoring deep sleep through behavioral and environmental interventions without medication has been shown to reduce subjective pain intensity in several clinical studies, sometimes significantly. Temperature regulation during sleep is not merely passive. The brain actively manages body temperature throughout the night, and the patterns are distinct across sleep stages. During NREM sleep, particularly deep sleep, the brain reduces its own metabolic heat production, contributing to the drop in core temperature during REM sleep. However, thermoregulation is temporarily suspended. The body neither shivers in the cold nor sweats in the heat. This is why sleeping in an overly warm or cold environment disrupts REM sleep disproportionately. The comfortable sleeping temperature that allows all sleep stages to proceed normally is relatively narrow. Research suggests a bedroom temperature between 60 and 67 degrees Fahrenheit is generally optimal for most adults. The duration of the first deep sleep cycle of the night is strongly influenced by how long you were awake before sleeping. This is the expression of sleep pressure, the adenosine-driven drive to sleep that accumulates with wakefulness. After a normal day of 16 to 17 hours of waking, the first bout of slow-wave sleep is dense and prolonged. After a shorter waking period, as after a long nap, it is correspondingly shorter. This is why sleep scientists generally advise against long naps. Late in the day, they partially discharge the sleep pressure that would otherwise be directed into the night's first deep sleep cycle, spreading the restorative work more thinly across the night. Researchers studying the effects of light on sleep have found that blue wavelength light, the kind emitted by screens, LED lighting, and many overhead lights, suppresses the release of melatonin and delays the onset of slow-wave sleep. Melatonin, produced by the pineal gland in the absence of light, is one of the signals that initiates the timing of the sleep cycle. When blue light exposure continues into the evening, melatonin release is delayed. The circadian signal for sleep onset is pushed later, and the first deep sleep cycle, already time-sensitive, begins at a less favorable point on the biological clock. The body's preparation for deep sleep is a process that begins well before the eyes close, and the light environment of the evening hours shapes it significantly. Deep sleep is profoundly influenced by mental habits formed over time. Minds that have practiced worry, rumination, or hypervigilance as their default mode of operation tend to have more difficulty transitioning into the synchronized, slow oscillation state of N3. The nervous system trained to scan for threats does not easily relinquish its vigilance at bedtime. Mindfulness-based practices, including body scan meditation, slow breathing, and progressive muscle relaxation, have been studied as tools for supporting this transition. Research suggests they work, at least in part, by activating the parasympathetic nervous system and reducing the cortisol and arousal levels that suppress slow-wave sleep. The practices are not dramatic. They are quiet, repetitive, and gentle, which is precisely what the transition into deep sleep requires. The timing of meals affects sleep architecture in ways that researchers are still mapping. Eating large meals close to bedtime elevates core body temperature and metabolic rate, both of which work against the cooling and slowing that precede deep sleep. Insulin and glucose dynamics also interact with the sleep system. High glycemic meals in the evening have been associated with more fragmented sleep and reduced slow-wave activity. Conversely, certain foods, those rich in tryptophan, the amino acid precursor to serotonin and melatonin, have been studied for their potential to support sleep, onset, and depth. The evidence for specific foods is modest, but the broader principle is well supported. The body arrives at sleep prepared for it, or not, depending on the metabolic state it carries in. There is a measurable relationship between deep sleep and the experience of waking up feeling restored. Researchers studying subjective sleep quality and polysomnography together have found that the proportion of time spent in N3 is one of the strongest predictors of how rested a person feels upon waking. This is not trivially obvious. Total sleep time, sleep onset latency, and number of awakenings all influence subjective restedness. But slow wave percentage remains a significant predictor even after controlling for these. People who obtain adequate deep sleep tend to describe waking as a gradual arrival into clarity. Those with reduced deep sleep more commonly describe waking into a kind of fog that lifts slowly. If at all, dreaming occurs predominantly in REM sleep. But slow-wave sleep is not entirely dreamless. When people are woken from N3, they sometimes report thoughts, not the vivid, narrative dreams of REM, but fragments of imagery, sensation, or simple ideas. These reports are typically brief and poorly organized, more like isolated impressions than stories. They lack the narrative coherence and emotional intensity of REM dreams. Some researchers suggest that cognitive activity during N3 may represent a quieter form of processing, less creative integration, more basic consolidation. What is consistent across studies is that whatever happens during deep sleep, it is rarely remembered in the morning. The brain does not encode its own maintenance work. The discovery that the brain has its own waste clearance system overturned a long-standing assumption in neuroscience. For decades, it was believed that the brain, unlike other organs, had no lymphatic drainage system, and that metabolic waste was removed through the blood-brain barrier alone. The identification of the glymphatic system in 2013 resolved a significant puzzle. How does an organ that generates as much metabolic waste as the brain, despite comprising only 2% of body weight, but using 20% of the body's energy, clear that waste efficiently? The answer, it turned out, required sleep. The glymphatic clearance system is most active during slow-wave sleep, when the spaces between brain cells expand by up to 60%, allowing cerebrospinal fluid to flow more freely through them. The relationship between deep sleep and learning was famously illustrated in a study that measured participants' ability to learn a new task before and after a night of sleep. Those who slept showed significant improvement the next day. Beyond what could be explained by rest from fatigue, those who were kept awake did not show the same improvement. More striking was what happened when the researchers selectively disrupted deep sleep while leaving total sleep time intact. Even with the same hours in bed, the participants whose N3 was disrupted showed substantially less learning consolidation. The brain needs not just sleep, but the specific architecture of deep sleep to transform the day's learning into lasting knowledge. Genetic factors influence how much deep sleep a person naturally obtains and how sensitive they are to sleep deprivation's effects on N3. Researchers have identified specific gene variants associated with higher or lower slow-wave activity, variations in the expression of adenosine receptors, and differences in the pace of circadian rhythms. This means that two people following identical sleep schedules and habits may experience meaningfully different amounts of deep sleep. One through natural predisposition, not through anything they are or are not doing. Sleep science increasingly recognizes this individual variation as genuine biology rather than difference in effort or discipline. Treating one's own sleep architecture as data, without judgment, is part of working with it rather than against it. The slow oscillations of deep sleep travel across the brain in a direction, from front to back, that mirrors, in reverse, the direction of information processing during waking. When you are awake and attending to something, information flows from sensory areas at the back of the brain toward the prefrontal cortex at the front, where it is integrated and acted upon. During deep sleep, the slow waves originate in the prefrontal regions and sweep backward. Some researchers find this reversal meaningful, as if the brain, having spent the day receiving and responding to the world, turns inward during sleep to review and reorganize what it has collected, beginning from the center of planning and judgment. People who report chronically poor sleep quality, even when their total sleep time appears adequate, often show reduced slow-wave activity on objective measures. This discrepancy between subjective and objective sleep quality is common enough that researchers use the term sleep state misperception to describe it. A person may feel they have not slept well, while polysomnography records a relatively normal night. The inverse also occurs, though less commonly. People who feel they slept well may show objectively fragmented sleep. In both cases, the experience of restoration appears linked not only to the quantity of deep sleep obtained, but to the continuity of slow-wave activity. Long, uninterrupted stretches of N3 appear to be more restorative than the same total time in fragmented episodes. Napping recovers some of the restorative functions of deep sleep, but incompletely. A short nap of 20 to 30 minutes typically involves only N1 and N2 sleep and produces genuine benefits: improved alertness, faster reaction times, better mood. A longer nap of 60 to 90 minutes allows the brain to enter N3, providing some slow-wave benefit. But even a well-timed nap cannot substitute for the sequential architecture of a full night. The early deep sleep cycles rich in N3, followed by the later cycles rich in REM. These stages are not merely adjacent, they are dependent. What happens in deep sleep in the first half of the night prepares the ground for what happens in the second half. The night is a whole. The brain uses slow-wave sleep to consolidate spatial memory, the mental maps that allow you to navigate familiar environments and form a sense of where you are in relation to the world. The hippocampus, which encodes spatial information as well as declarative memory, replays spatial sequences during deep sleep in the same compressed or accelerated fashion that other memories are replayed. Studies of rats navigating mazes have provided some of the clearest evidence of this process. As the firing patterns of hippocampal place cells during slow-wave sleep precisely replay the paths the animals traveled during waking, Human neuroimaging studies have identified analogous replay processes, suggesting that the spatial knowledge built during a day, a new route, a new space, a new mental landscape, is consolidated overnight. Deep sleep declines more sharply in men than in women across the lifespan. According to several large studies of sleep architecture across age groups, women tend to maintain higher slow-wave activity into middle age. And some researchers have proposed that this may be related to differences in hormonal regulation, particularly the role of estrogen and progesterone in supporting deep sleep. This advantage appears to reduce after menopause, at which point women's deep sleep patterns tend to converge more closely with men's. The reasons for these sex differences are not fully understood, and research in this area continues to develop. What is consistent is that individual variability within sexes is larger than the average differences between them. One of the most peaceful facts about deep sleep is this: it is happening whether you think about it or not. You cannot directly observe your own slow waves, cannot feel the glymphatic system working. You cannot sense the hippocampus replaying the day's learning. The machinery of deep sleep runs beneath consciousness entirely. What you can do, all you can do, is create the conditions for it. A consistent schedule, a cooling room, a quieting of the day's activities before bed, the willingness to lie down and release the day, not because it is finished, but because the work of sleep requires that you stop working. Deep sleep does not need your guidance. It only needs your permission. Allow your thoughts to soften now. You don't need to hold on to any particular idea, whatever you were thinking about before tonight. The list, the question, the thing unfinished. It will still be there tomorrow, if it matters. But right now, there is only this: the soft weight of your body, the quiet pace of your breath, the room around you, dark and still and safe. You are somewhere between one world and another now. Let yourself drift a little further. The deep is not far. The brain's electrical activity during deep sleep has been described as the most organized state the brain ever enters. When you are awake, the brain's electrical patterns are complex, variable, and high frequency, reflecting the constant processing of sensory input, thought, and response. In deep sleep, this complexity gives way to a single, sweeping rhythm, unified across vast areas of the cortex. Neuroscientists sometimes describe this as the brain settling into a common language. A brief moment when disparate regions stop their independent activity and move together. It is both the simplest and, in some ways, the most powerful state the brain produces. Sleep researchers sometimes use a term borrowed from engineering to describe what slow-wave sleep does for the brain's signal-to-noise ratio improvement. During waking hours, all synapses receive approximately equal maintenance. The neural network is biased toward keeping everything activated and available. During slow-wave sleep, the most used connections are preferentially preserved, while the least used are gently quieted. The result, come morning, is a brain in which the signals that matter, the connections most relevant to learning, habit, and identity, stand out more clearly against the background of less relevant activity. Deep sleep, in this sense, doesn't just restore the brain, it sharpens it. The slow waves of deep sleep are sometimes called traveling waves because they do not occur simultaneously across the entire brain. They move. A slow wave typically originates in the medial prefrontal cortex, then travels backward through the brain, reaching the parietal regions and eventually the occipital cortex. This traveling nature was revealed by high-density EEG recordings using hundreds of electrodes simultaneously, which allowed researchers to track the spatial progression of each wave. The discovery changed how scientists think about slow-wave sleep, not as a uniform global state, but as a dynamic process with direction, timing, and spatial organization that varies from wave to wave. Deep sleep appears to play a role in regulating insulin sensitivity, the body's ability to respond efficiently to the hormone that manages blood glucose. Studies in which healthy adults had their slow-wave sleep selectively disrupted, using sounds timed to prevent the deepest oscillations without fully waking the subjects, found measurable reductions in insulin sensitivity after only 3 nights. The effect was comparable, in some studies, to the metabolic impact of gaining 20 to 30 pounds. This finding has contributed to growing scientific interest in the relationship between sleep quality, not just sleep duration, and metabolic health, and to the recognition that deep sleep is a significant variable in long-term disease risk. The theta rhythm, a brain wave frequency of 4 to 8 cycles per second, is prominent in the transition stages between waking and deep sleep and during REM, but during the slow oscillations of N3, the brain produces something more coherent and lower in frequency, the delta rhythm, which is not merely slower than theta, but structurally different. Where theta is associated with active memory retrieval and navigation, delta is associated with restorative disengagement. The brain stepping back from active processing into a state of organized maintenance. Listening to the brain's frequencies is, in a sense, listening to the different kinds of work it does. Slow and deep is not the same as stopped. The concept of sleep architecture refers to the specific pattern of sleep stages across a night. How much time is spent in each stage? In what order? And with what transitions between them? Sleep architecture is not random. It follows a predictable and remarkably consistent pattern across most healthy adults under normal conditions. The night is divided into cycles of approximately 90 minutes each. Early cycles are weighted toward N3. Later cycles shift toward REM. Understanding your own sleep architecture, even at a general level, can help make sense of the difference between a night that restores and one that does not. When the body is fighting an infection, the immune system produces cytokines that promote slow-wave sleep. This is not coincidental. The immune system has, in a sense, I learned that deep sleep is when the resources it needs are most available. Growth hormone, released during N3, supports immune cell proliferation. Body temperature regulation during deep sleep supports the thermal environment that immune processes prefer. Even the reduced metabolic demands of deep sleep redirect energy toward immune function. The impulse to sleep when sick is not weakness. It is the body intelligently requesting the conditions under which its defenses work best. Researchers studying the effects of mindfulness meditation on sleep have found that experienced meditators show increased slow-wave activity compared to non-meditators with similar sleep durations The proposed mechanism involves the long-term structural changes that meditation produces in the prefrontal cortex, the region most associated with generating slow waves. Chronic practice of meditation appears to support the neural architecture that underlies deep sleep. In addition to its well-documented effects on stress and emotional regulation, this suggests that the benefits of meditation on sleep are not limited to making it easier to fall asleep, but may extend to improving the quality and depth of the sleep itself. The glymphatic system's activity peaks not only during sleep, but specifically during slow-wave sleep. Measurements of cerebrospinal fluid flow have shown that the rate of glymphatic transport increases during N3 compared to both waking and REM states. This finding points to the deep stages of sleep as the primary window for brain waste clearance, and has led researchers to ask whether fragmented sleep that moves through the cycles without spending adequate time in N3, results in meaningful accumulation of waste molecules, even when total sleep time appears normal. The evidence is not yet conclusive, but the directionality is consistent: more deep sleep, cleaner brain. There is a measurable signature in the sleeping brain that appears to reflect individual differences in intelligence and learning capacity. Researchers have found that the density of sleep spindles, those brief oscillatory bursts in N2 and N3, correlates with performance on tests of fluid intelligence, memory consolidation, and cognitive flexibility. This correlation holds even after controlling for age and total sleep time. It is not that smarter people sleep differently by accident. Rather, sleep spindles may be one of the mechanisms through which cognitive capacity is built and maintained. The brain that spins more spindles may literally be doing more of the neural work that underlies learning. Slow-wave sleep is when the brain consolidates procedural knowledge, the implicit, automatic knowledge of how to do things. This is distinct from the declarative knowledge encoded in the hippocampus. Procedural memory is stored in networks involving the basal ganglia and cerebellum, and its consolidation during sleep follows a somewhat different time course than declarative memory. Learning a new sequence of movements, for example, continues to improve overnight. And this improvement is correlated with the amount of slow-wave sleep obtained. Researchers studying music students, athletes, and people learning complex manual skills have consistently found that sleep between sessions produces gains that waking practice alone does not. The science of chronobiology, the study of biological rhythms, identifies the timing of deep sleep as strongly regulated by the circadian clock, the internal clock, housed primarily in a small region of the hypothalamus called the suprachiasmatic nucleus, coordinates the timing of hundreds of biological processes, including sleep onset, slow-wave activity, growth hormone release, and immune function. This timing system is entrained to the external light-dark cycle, consistency of sleep timing, going to bed and rising at similar times each day, supports the clock's precision, which, in turn, supports the timing and depth of N3. The circadian system does not merely prefer consistency, it performs best with it. Polyvagal theory, a framework proposed by neuroscientist Stephen Porges to describe the hierarchical organization of the autonomic nervous system, suggests that the state of the vagus nerve and its branches influences both the quality of sleep and the ease of transition into it. Eye vagal tone, associated with a regulated, safe nervous system state, correlates with greater heart rate variability, and has been linked to better sleep architecture, including more time in slow-wave sleep. This is one of several frameworks connecting the body's threat detection systems to sleep quality. It is worth noting that polyvagal theory remains partially contested in the scientific literature, though its clinical applications in stress and sleep continue to be actively studied. Researchers have found that the quality of social connection during the day influences sleep architecture at night. People who report greater feelings of safety and belonging show higher slow-wave activity. Those experiencing social isolation, loneliness, or chronic interpersonal conflict show more fragmented sleep with reduced N3. The nervous system's threat detection system is calibrated partly by social context. A body that feels socially safe is more capable of the sustained parasympathetic state that deep sleep requires. This research has grown more prominent in recent years, contributing to the scientific understanding that sleep is not purely an individual biological event, but is embedded in the social and relational environment. Light falling on the retina in the morning activates the suprachiasmatic nucleus and sets the circadian clock for the day. This morning light signal determines, in part, when melatonin will rise in the evening, which in turn influences when slow-wave sleep will peak. A person who gets bright morning light exposure typically has an earlier melatonin rise and an earlier onset of deep sleep. This downstream relationship means that what you do in the morning, whether you encounter bright outdoor light or remain in dim indoor conditions, is reaching forward across the entire day to shape the quality of the night that follows. Recent research has explored the role of deep sleep in regulating fear memory and fear extinction, the process by which conditioned fear responses are reduced over time. Animal and human studies suggest that slow-wave sleep facilitates the consolidation of extinction learning. The neural memory that a previously feared stimulus is now safe. Disrupting deep sleep after extinction training impairs this consolidation, allowing fear responses to return more easily. These findings have implications for understanding and treating anxiety disorders and trauma, where the normal process of fear regulation through sleep may be disrupted, potentially perpetuating the heightened threat responses that characterize these conditions. The word restoration is used often in describing what deep sleep does, but it understates the precision of the process. It is not that the brain simply rests and recovers. It is that specific molecular, synaptic, and cellular processes occur during specific phases of the sleep cycle that cannot occur otherwise. Certain proteins are synthesized during sleep that are not synthesized during waking. Certain synaptic modifications require the altered neurochemical environment of N3. The brain does not merely pause during deep sleep and resume upon waking. It completes processes that were scheduled for this window, processes that, if the window is missed, will simply not be completed. The brain's default mode network, a set of regions that become active when the mind is at rest or engaged in self-referential thought, shows a distinctive pattern of activity during sleep. During waking, the default mode network activates during daydreaming, autobiographical memory retrieval, and social reasoning. During deep sleep, this network undergoes a form of disconnection. Its regions cease their coordinated activity and fall into the general synchrony of slow oscillations. Some researchers have proposed that this disconnection is what creates the subjective experience of dreamless deep sleep. The absence of self-awareness, narrative, and continuous thought that characterizes the deepest stages. There is a phenomenon in sleep science called slow-wave sleep rebound. The brain's tendency to compensate for lost deep sleep by producing more of it in the next available sleep opportunity. If a person has a night of significantly reduced N3, the following night will typically show an increase in slow-wave activity, concentrated especially in the first cycle. This rebound is not complete. Not all lost deep sleep is recovered. But it reveals that the brain tracks its own slow-wave debt and responds to it. The biological need for deep sleep is specific and persistent. The brain does not forget what it missed. The relationship between deep sleep and the sense of time is unusual. Time perception during N3 is absent. There is no subjective experience of duration, no sense of minutes passing. This is consistent with the disconnection of the cortex from sensory and thalamic input during deep sleep. But it has an interesting implication. The restorative work of deep sleep is done in what feels like no time at all. From the inside, the night's most productive biological hours are simply missing from experience. You fall asleep, and then it is morning. What happened in between? The slow waves, the glymphatic clearing, the memory consolidation, is entirely invisible to you. Music and sound environments have been studied for their potential to support sleep onset and deepen sleep architecture. Research suggests that continuous, low-frequency, non-rhythmic sounds, such as rain, flowing water, and certain forms of ambient music, can mask environmental noise disruptions that might otherwise prevent the transition into N3. Beyond noise masking, some frequencies of sound have been found to affect autonomic nervous system activity, slightly lowering heart rate and reducing cortisol in the minutes before sleep. The effect is modest, but consistent across several studies. The body responds to the acoustic environment, even as it prepares to disengage from it. There is evidence that the brain, during slow-wave sleep, performs a kind of pruning not only of synaptic connections, but of emotional associations. Memories that carry significant emotional weight when first formed tend to be recalled with less emotional intensity after a full night of deep sleep, even when their factual content is well preserved. This process has been called sleep-dependent emotional memory processing. It may explain, in part, why difficulties that feel acute and overwhelming late at night often seem more manageable in the morning. The night has literally done something to the emotional coating of the experience, softening its edges without erasing its content. The brain waves of deep sleep have been measured and found to synchronize across different regions of the brain in ways that vary throughout the night and across individuals. This synchrony, the degree to which different regions oscillate together, is thought to reflect the efficiency of information transfer between brain areas during the consolidation processes of N3. Higher synchrony is associated with better memory performance the following day. Individual differences in synchrony may partly explain why some people consistently feel more restored after the same amount of sleep than others. Not a difference in sleep quantity, but in the coordination of what happens within it. The question of whether you are getting enough deep sleep is genuinely difficult to answer without measurement. Most people have no reliable way to know how much N3 they are obtaining each night. Consumer sleep trackers provide estimates, but their accuracy in measuring specific sleep stages remains limited compared to laboratory polysomnography. What is more accessible is the subjective and functional signal of deep sleep quality. Do you typically wake feeling rested? Does your cognitive performance feel consistent across the day? Do you recover quickly from physical and emotional demands? These questions are imperfect proxies, but they point toward the same underlying biology that laboratory measures reveal. Deep sleep is when your brain quietly clears, repairs, and files away everything from the day, and it works best when you stop trying to control it. This is perhaps the most paradoxical thing about deep sleep. The people who pursue it most anxiously often obtain it least well. The aroused, effortful search for rest is physiologically incompatible with the state it seeks. Deep sleep arrives in the absence of effort, in the spaces between thoughts, in the release of the day's concerns. In the body's quiet, willingness to be carried somewhere it cannot follow consciously. It does not come to a mind that is grasping. It comes to a mind that has set down everything it was holding. Let your body be completely still now. Not still because you are trying to be still. Still because there is nothing left to move toward. The day is done. Whatever it held, it is behind you now. Your brain has already begun its quiet work. The work you will never see and don't need to see. You can let yourself be carried. You don't need to navigate. You don't need to remember the route. The deep is just ahead. You have been moving toward it all night. Slow wave sleep typically begins within the first 30 minutes of falling asleep in a healthy adult. The transition into N3 is gradual. The brain moves through N1, then N2, and the slow waves begin to appear and deepen. The first fully formed slow wave period of the night is usually the longest and deepest. Whatever supports you in falling asleep smoothly and continuously, the dark room, the cool air, the quieted mind, is supporting the depth of this first descent. The body's core temperature reaches its lowest point of the 24-hour cycle during deep sleep. This cooling is not accidental. It is one of the conditions that make slow wave activity possible. A body that remains too warm will cycle through lighter sleep stages without descending deeply. The room around you right now, if it is cool, is doing something useful. The air on your skin is helping the night do its work. Growth hormone released during deep sleep supports the repair of tissues throughout the body, not only muscles and bones, but the cellular lining of blood vessels, the integrity of skin, and the maintenance of the immune system's structural components. This release occurs in a single large pulse early in the night. It is the body's primary maintenance window, and it runs on the schedule of slow-wave sleep. The night is not empty time. It is the workshop. The hippocampus replays the day's experiences during slow-wave sleep in a compressed, accelerated form. Sequences that took minutes during waking are replayed in seconds. This compressed replay allows the brain to process many experiences in a relatively short window. The memories most likely to be replayed are those tagged with relevance, by emotion, by novelty, or by repetition. The sleeping brain is not neutral. It is curating. The prefrontal cortex generates the slow oscillations that give deep sleep its character. This is the same region responsible for planning, decision-making, and emotional regulation during waking. It is, in a sense, the last part of the brain to fully disengage at night, and the first to show signs of impairment when deep sleep is insufficient. The relationship between the prefrontal cortex and deep sleep is circular, and sustaining the cortex generates the waves that restore it. Sleep spindles, brief bursts of synchronized activity in N2 and early N3, protect deep sleep from disruption. They act as a kind of buffer, filtering out sounds and sensations that would otherwise break the transition into slow-wave sleep. On nights when the sleeping environment is noisier than usual, spindle activity tends to increase, the brain working harder to maintain its own quiet. The effort is mostly invisible. You sleep through what would have woken you. And in the morning, you do not know how much of that was the brain's doing. The amount of slow-wave sleep a person needs does not change much across adulthood, but the ability to obtain it often does. A. Stress, irregular schedules, and environmental disruptions all reduce N3 without reducing the biological requirement for it. This gap between what the brain needs and what circumstances allow is one of the quieter sources of cumulative fatigue that many people carry. The need does not diminish simply because the supply is reduced. People who are blind from birth show normal sleep architecture, including normal slow-wave activity. The circadian clock is entrained by light in sighted individuals, but the deep stages of sleep themselves do not depend on visual input. The slow oscillations of N3 arise from within the brain's own circuitry, from the interplay between the thalamus, the cortex, and the neurochemical environment of sleep itself. Deep sleep is not a response to darkness. It is an internal event that darkness merely accommodates. Some of the research on deep sleep and Alzheimer's disease has moved toward intervention. Scientists are exploring whether enhancing slow-wave sleep through acoustic stimulation, temperature modulation, or other means can meaningfully increase glymphatic clearance of amyloid beta in older adults. Early results are cautiously encouraging. They represent a shift in perspective. From viewing deep sleep decline as an inevitable consequence of aging, to asking whether it might be partially modifiable, and whether doing so might matter for long-term brain health. Every time you have woken up feeling genuinely rested, alert without effort, clear without caffeine, present without struggle, you have experienced the result of sufficient deep sleep. It does not announce itself. It simply makes the morning feel like the morning is supposed to feel. That quality of waking, when the world comes into focus without friction, is not accidental. It is the signature of a brain that has done its work. The experience of lying in bed, unable to sleep while the mind continues racing is, neurologically, a state of cortical arousal that is physiologically incompatible with slow-wave sleep. The brain is producing beta waves, the high-frequency signature of active, effortful thought. When it needs to be descending toward delta, the transition cannot be forced, but it can be invited by reducing arousal, by releasing the effort of trying, by allowing the body's own drive towards sleep to operate without interference. The amount of time the average adult spends in N3 each night has been estimated at between 60 and 90 minutes, distributed across the first 2 sleep cycles. This is roughly 1 to 1.5 hours out of a 7 or 8 hour night. A small proportion, perhaps, but a disproportionately influential one. Much of what the night does for you happens in that window. The rest of the night, the lighter stages, The NREM cycles is valuable, but it is different work. The deep is where the most essential maintenance is done. Your brain waves right now, if you are drifting, may already be slowing. The theta waves of drowsiness, cycling at 4 to 8 times per second, are a bridge between waking and sleep. They carry with them the floating, loosened quality of thought that precedes sleep. The half-images, the softened logic, the slow dissolution of the day's preoccupations. You may be closer to your first slow wave than you know. The quality of the night's sleep often reflects the quality of the transition into it. A body that approaches sleep with physical tension, a mind that approaches it with unsettled thoughts, a nervous system that approaches it with elevated arousal. These are bodies that will spend more time in the lighter stages before descending. The transition is not instantaneous. It is a negotiation between the day's residue and the night's invitation. The more completely the day can be released, the more completely the night can arrive. The words for deep sleep across different languages often carry connotations of depth, weight, and descent. In French, sommeil profond, profound sleep. In German, Tiefschlaf, deep sleep, literally. In Japanese, Yaumin, heavy sleep. Across cultures, the metaphor is consistent. Deep sleep is not merely a biological state, but an image of going somewhere far down, somewhere below the surface of ordinary experience, where the self is held in something larger and quieter than itself. The restoration that follows deep sleep is not only cognitive. Athletes show faster muscle recovery, reduced inflammatory markers, and better coordination. After nights of adequate slow-wave sleep, students show better retention of studied material. People with mood disorders show greater emotional stability. The brain and body are not separate systems that sleep affects independently. They are one system, and deep sleep addresses them together in the same nightly window. Through processes that are interconnected at the cellular level, there is a simplicity on the other side of all this complexity. The science of deep sleep is intricate. Delta waves and glymphatic systems and synaptic homeostasis. But what it points toward is not complicated. Your brain knows how to sleep. It has been doing this your entire life. Every structure needed, every system required, every wave that needs to roll, it is already there. All of this happens when you stop holding the day. The science is the reason. The invitation is simply let go. The practice of sleep hygiene, the collection of behavioral and environmental habits that support sleep quality, is, in biological terms, a practice of supporting the conditions for deep sleep specifically. A consistent schedule supports the circadian timing of N3. A cool environment supports the temperature drop that precedes it. A quiet, dark room supports the sensory gating that protects it. These are not arbitrary recommendations. They are the environmental conditions under which the brain's slow-wave architecture functions best, derived from understanding what deep sleep actually requires. Research on insomnia has found that cognitive behavioral therapy for insomnia, known as CBTI, is more effective than sleep medication for improving both sleep onset and sleep quality, including slow-wave sleep. In the long term, one of the core components of CBTI is sleep restriction. Temporarily limiting time in bed to consolidate sleep pressure and improve sleep continuity. Another is stimulus control, training the brain to associate the bed with sleep rather than wakefulness. Both approaches work partly by improving the conditions under which deep sleep can occur. The fact that you are here tonight, listening to this, is already part of the preparation. A mind that is gently occupied by calm, by curiosity, by the slow unfolding of something interesting, is a mind that is releasing its daytime mode without forcing it. The science has been a vehicle. The destination is the same place it always is. Somewhere below language, below thought, below the reach of effort, your brain knows the way. In the deepest seconds of N3, the brain is further from the experience of being a person than at almost any other point in life. No narrative, no self-awareness, no distinction between what is inside and what is outside. Just the slow, synchronized oscillation of millions of neurons moving together through the dark. Some philosophers have found this notable, not frightening, but profound. The self, so vivid during waking, quietly disappears each night. And each morning, it returns, a little refreshed, a little cleared, as if the absence itself had done something good. The science of deep sleep is ultimately a science of trust. The brain cannot be commanded into slow-wave sleep. The glymphatic system cannot be switched on by willpower. Memory consolidation cannot be accelerated by trying harder. All of it requires surrender, the body's willingness to let go of the waking mode and enter the one it was made for. The trust is biological before it is psychological. Your body knows how to do this. It has never forgotten. Tonight, as you drift closer to your first slow wave, the work of the day will begin to be received and filed and cleared. You will not be there to witness it. You will not remember it, but it will have happened. And in the morning there will be evidence of it. In the clarity of thought, in the lightness of the body, in the way the world comes into focus without effort. The night keeps its own record. Your brain is already slowing. The thoughts that seemed pressing an hour ago are becoming smaller, more distant. The slow oscillations may already be beginning at the edges of your awareness. The loosening of the day's grip, the softening of the boundary between what is real and what is drifting. This is the threshold. You have been moving toward it all night. It does not require anything more of you. Just this stillness, just this breath, just this moment, and then the next one, and then the one after that. What is your brain actually doing when it finally reaches deep sleep? It is clearing. It is repairing. It is consolidating everything that mattered. It is rebuilding the architecture of tomorrow from the materials of today, and it is doing all of this quietly. In the dark, without you, deep sleep is when your brain quietly clears, repairs, and files away everything from the day. And it works best when you stop trying to control it. You already know how to do this. You have known your whole life. Tonight, simply let it happen. Tonight, we traveled from the first electrical signature of deep sleep, the rolling delta waves sweeping front to back across the cortex, all the way to the quiet truth at the center of it all. We learned that the brain clears its waste during slow-wave sleep through a system that only activates in these hours. We learned that memories are replayed, compressed, and transferred while consciousness is entirely absent. We learned that deep sleep is not passive rest, but the brain's most purposeful state. And perhaps most of all, we learned that the deepest restoration happens not when we try harder, but when we let go. Sleep is not time taken away from life. It is where life is maintained. Every night, in the silence that most people simply pass through without knowing, the brain does its most essential work. You have been here, in that silence, your whole life, and it has been taking care of you. There is nothing left to understand tonight. Nothing left to hold on to. Let your breath be slow and easy. Let your body feel the weight of stillness pressing gently from above. You are already somewhere quiet inside yourself. The night has you. The slow waves are coming, or they are already here. You don't need to meet them. They will find you. Rest now. Rest well. If this quiet journey through the science of sleep helped you find rest tonight, a gentle like or subscribe helps other sleepless minds find their way here too. It only takes a moment, but it means the world to us. One sleepy soul at a time. But there's no need to do anything now. Nothing at all. You've traveled far tonight, through the hidden machinery of the sleeping brain, through the science of what happens when the mind finally lets go. You can allow all of it to drift away now, like slow waves fading into stillness, leaving only the quiet behind. Let your breathing deepen. Let your body grow heavier, as if the night itself is gently pressing you down into rest. If sleep comes, let it carry you, smoothly, quietly, into the deep that has been waiting for you all evening. If your eyes are still open, the next video is ready when you are. But if they're closed, stay there. Tomorrow, the brain will do it all again. But tonight belongs to stillness. Rest well, quiet mind, and remember, deep sleep is not something you achieve. It is something you allow. Good night.